Okay, so today we are going to talk about visual perception, and specifically we're going to talk a lot about mapping data to visual properties. Okay, we'll also talk about the data to ink ratio and some do's and don'ts, which are all rules of thumb and should not be treated like golden rules. All right. So the primary learning objective is to understand how specific decisions that you make can help or hinder the comprehension of others to your plot. All right. And again, like all of this is fuzzy. So there are things that in most situations will make your chart better able to be comprehended by a wider audience. But in specific circumstances, depending on who the audience is, what their background is, etc., it might be better to do other things. Okay, there are a couple things that I'll show you near the end, which I'm guessing we probably actually won't get to today because we're already half an hour in. But there are a few things that are like never do, right? But the vast majority of them are sort of probably don't do this or probably do this, but like it's all fuzzy. And that's part of what I think is kind of fun about data visualization is a lot of it is sort of like there is research on these things in terms of what works best and whatever, but there's also it's context dependent, and there's a lot of sort of artistic license that goes into all of this too. Okay. Every time I give this talk, I always feel like I have to give this disclaimer to start because I almost always am giving this talk to a bunch of psychologists like I am today. So I have to give the disclaimer that I am not a psychologist. All right. So I don't really know why we perceive some of the things the way that we do or don't, but we do perceive things differently, right? And so basically what I'm trying to illustrate here is that different things work better than others. And so your visualization should account for those things, right? And you should be cognizant as you're building these in terms of what does work well and what doesn't, what tends to work well and what doesn't. So to start out, there are a number of different visual cues that you can use when you're building a data visualization. These are roughly ordered in how well we perceive them. Okay, this is not perfect, and there's some debate about them, but generally, position is going to work really, really well, right? So if you have two things on the same axis and you're looking at how far apart they are, we tend to be really good at that. Length in one dimension we're also quite good at that. Angle tends to be a little more difficult, right? So what's this angle versus this angle, right? And how much does that really mean, right? That's a little bit more difficult. And then direction like a slope. So if you have a time series, like what's this slope versus this slope, and is that meaningful? That's a little bit harder also. There's also shapes, which work really well for categorical data, but basically don't work for continuous data, right? And then there's area and volume, which are basically how big in 2 or 3 dimensions. And that starts to get really tricky. The main thing that you want to avoid with those is, and a common error is that you have like a box, which has 2 dimensions, but then it scales up by 1 dimension, by 1 variable, and that 1 dimension, and that can lead to visual artifacts, all right? Shade and color are on the bottom, and that is mostly because of color blindness. All right, so color blindness is a lot more prevalent than I think people realize. About 10% of the male population has some form of color blindness, and so and for females it's much less, but it's still, if you're talking about the overall general population, it's a good amount of people. It's like 8-9% of all people. Okay, so so shade and color are really, really effective tools, and we're going to use them, but you have to be very careful about how you use them, because if you use them incorrectly, it's going to be inaccessible to a wide range of people, right? And one of the best ways to get good at this is to work with somebody who has some color blindness, because you will build something that you think is great and show it to them and they can't make heads or tails of it, right? There are other ways, though, that we'll talk about where you can sort of mimic those things. So we have a whole week that's on color, and I think it might even be next week. And so we'll talk a lot about that stuff then, okay? So when you're encoding data, you can encode it a bunch of different ways, right? The first way is position, right? That's the X, Y. And again, that's going to be super effective most of the time. Then we have shapes. That's going to work for categorical data, but not for continuous data. But a single shape can be encoded with a continuous variable, right? So looking at that circle getting bigger, and we just saw that in some of the visualizations in the data viz, in the wild thing, right? Color, lines, line type. So again, lines can be encoded relative to a continuous variable, but the effectiveness is, I don't know, it would depend, but generally is not going to be great, right? Because look, how much different is this line versus this line, right? And then this is an example where lines are encoded to a categorical variable. These are categorical as well, but color can be continuous also. There's also a bunch of other elements that you're going to want to consider when you're building your visualization. Chief among them is text, okay? So almost all of the visuals that you'll build will have some form of text, usually the title. I just talked about how important the title can be. So you'll want to think about how is the text displayed. And again, the one plot in that I pointed out during the data viz in the wild ones had a great use of color within that title to help draw your eye to this specific thing I was talking about, right? And we'll see examples of how to do exactly that. But think about the purpose of the text, where it should be on there, use accessible fonts, those sorts of things. Again, we'll talk about this stuff more later. Transparency. Transparency can often help, but you have to be careful about it again. If there are overlapping pieces in particular, that's where transparency can really help, because then you could, if you have, think of like a scatter plot that's really high density, right? Like there's a ton of points on there. Adding a little bit of transparency to those points can help you see sort of the distribution of those points in that XY space, okay? Whereas otherwise it might just look like a blob. And then the type of data. So this is obviously, you should always be thinking about this. Do you have continuous or categorical data? And then once you know that, like what aesthetic can each of those be mapped to? So as I was talking about before, shape and line can be mapped to categorical data. Well, not only be mapped to categorical data, because we could have a shape that increases in size, but generally, like if you're having different shapes, then that's going to be a categorical variable, right? You can't map a continuous variable to different shapes, at least not any way that I can think of that would make any sense. Whereas like color and size, right? Those can be categorical or continuous, right? Either one is going to be fine. All right, so what I'd like to do now is I will put you in breakout rooms, and then I want you to spend just a minute here. I'll give you like 2 or 3 minutes. Look at this data, and then try to figure out how you would encode these columns of data. Now, this has month and day, so I'm not wanting you to treat these as separate. Just think of this as like a single column called date, all right? And then you've got the location, station ID, you can include that or not, but basically I'm wanting you to say, okay, you got some time variable, a location, and a temperature, all right? So how would you map that data to some aesthetics, okay? All right, so that was quick, and some of you may not have gotten all the way through. One of the things I should have mentioned before we left is we're going to imagine that these are the only 4 cities that we have. Okay, so this is not every city in the country or whatever. So it's just these 4 cities. So how is one way that we could visualize this relation between basically time, the date, the location, and then the temperature.
I think we had a question, Daniel.
Mm-hmm.
Could we also assume that like it looks like each station ID is unique to that city? So are those considered like one variable together as well?
Sure.
Okay. Well, our group had um, date on the x-axis, temperature on the y-axis, and then different color lines, but being friendly to color blindness,
Mm-hmm.
representing location with like maybe connected dots, like a line that has connected dots, if that
Yeah,
makes
great. I love it. So basically, you're mapping um, date to the x-axis, temperature to the y-axis, and then location to color. And then you're doing points and lines across there, right?
Yes.
Any other ideas? Or is that basically what everybody kind of came up with?
We had a pretty similar thing where we thought about having like an animated line graph that as time was passing, you could just watch these lines crossing over each other.
Mm-hmm.
I think pretty similar to what Sarah's saying.
Yeah. So you'd want to add one more line with the GG animate package, and then you could watch the lines go.
Yep.
Great. So real quick, scales are going to define a unique mapping between data and aesthetics, right? And this has to be a one-to-one mapping, otherwise it becomes ambiguous. So we just talked about this, but in the previous one, when we're thinking about data values corresponding to specific aesthetics, right, we're thinking about time and temperature both corresponding to basically space, right? And then like where it is, and then this is going to be, the location is going to be mapped to color, right, or line type or whatever, right? There are quite a few different scales. These are some basic scales, right? Position, this is probably the most important, the one that we use the most, and that's what we would have had in our previous example, right? Position for the X and the Y axis, and then color, categorical version of color. This is showing a continuous version of color, but a categorical version of color for the lines, right? And then we would end up with something that looks like this, right? This is basically exactly what we were talking about, right? This one doesn't have the points, but otherwise it is what we suggested, right? And to do this with ggplot, we would just, I have this object in my environment called temps long, which basically looks exactly like the data that we had, right? And then we have a date variable, which I'm putting on the x-axis, temperature on the y-axis, and then you just use geom_line. And notice I'm using AES because I'm going to access a variable in my data set. I'm mapping my data to an aesthetic, right? And so I'm saying color is equal to location, all right? And that gets me there, all right? Now, this is the basic code for that plot, right? Doesn't look as nice as this one, I would argue, but it's the basic code. If we want to change colors, we have to change the scale, right? Because color is being mapped to, or sorry, location is being mapped to the color scale, all right? So we have to change the color scale, and oh shoot, did I not push those changes? I did not, shoot. I thought I did. Let me do this really quick. This is on my local. I realized I had that error right before class, and I meant to fix it, but apparently I did not. Okay, so this is the code that we would use to change the color, all right? So we have back here, this is our basic code, and then we want to change the color scale, right? So we're going to add another layer to our plot that says scale color, and then we have a whole bunch of different options from there. Okay, again, we'll talk about this more next week, but we have scale color brewer, scale color manual, scale color viridis, scale color continuous, scale color, all sorts of different things, right? And so here I'm using scale color brewer, which is just a series of palettes, and I'm saying change the palette to dark 2, and then I get this one. Okay, so that's a way that we would change the color. A couple important points here, though. You do not use scale color whatever if you are not mapping data to color. All right, so if you are not calling color within AES, basically, then you don't use scale color, right? Then you're just going to change the colors manually within those layers. The other thing to be careful of is if you're mapping data to colors and fills, then you need to make sure you keep that straight, right? Very often I end up in a situation where I'm mapping data to both a color and a fill. And then if I want to change those, I got to say scale color, whatever, plus scale fill, whatever, right? So if you're using a fill, then you need to use scale fill, whatever, not scale color, whatever. Okay, so that's a really common error where it's like, you know, I have changed these things, but when I'm using my scale color, whatever, it's not, the change isn't happening. And that's because you don't actually have color mapped to your aesthetics. You have a fill mapped to your aesthetics, or vice versa. Okay, this is an alternative representation of that exact same data source, right? The exact same plot. This is what I was talking about, Chris, when I was saying you would see an example of that. This has now a discrete x variable, x-axis, a discrete y-axis, and color is mapped to a continuous scale. Okay, so here we're looking at just basically average temperatures for each month, right? And then the fill is mapped to color. So this is brighter, that means it's a higher temperature. Okay, that makes sense? So this is a heat map. And if we wanted to create something like this, we would have to first take that temps long object, right? Then we're going to group by location and month. So location and month. And we're going to say the temperature is equal to the mean temperature, right? So the average temperature for the month. And then we're going to pass that to ggplot, put month on our x-axis, so it's a categorical variable now, and then location on our y-axis, and then we use geom tile to create these little squares. And then I like to use chord fixed with it as well, because I think that makes it nice with squares, right, instead of rectangles. And then you just say AES fill equals temp, and then notice I'm putting color equals white outside of that. So that's giving each square a white border so that they're more distinguishable, right, as unique squares. But the fill is according to the temp. Okay, and then again, if I wanted to change that fill, I could do so with plus whatever. Okay, in this case, I'm just showing an example of using a color palette from an external package. So there's this Sicko package by Thomas and Peterson that I think is quite good. He is crazy amazing. He does all sorts of awesome stuff. But this is a palette called Tokyo from that package, right? And so you use it just like ggplot, scale, fill, whatever, but it's scale, fill, Sicko. And then palette equals Tokyo, and now we get something like this. Okay, again, this is sort of artistic license, I would say, in terms of what fill you like the best, with the exception of it should be a fill that works well for color blindness, right? And I actually have no idea if this one does or not. I didn't check it. So, okay, comparisons. So both the line plot that we had and the heat map that we had both represent 3 scales, right? We have 2 position scales, the x and the y axis, and 1 color scale. But in the first plot, we had continuous x and y and categorical color, right? And in the second one, we have categorical x and y and continuous color. Does that make sense? Any questions on that? Okay. So more scales are possible. So here's an example where we're just looking at, I think, the highway miles per gallon one. But you have all of these points, it's a scatter plot, right? And the shape is, this is probably empty cars. The shape is the cylinders, the size of the shape is the weight, and then the color is the power. And then you're showing this overall relation. Is this effective? I don't know. Probably not really. This is the problem, right? Unless you have a lot of structure in your data, additional scales can get lost pretty quickly, right? And so I know this is small, but if we look here, right, on this side, it's almost impossible to make out those different shapes. And if there's any relation among them, I don't see any relation among them. So in that case, I'm not sure that you're gaining anything by adding that additional shape variable, right? Shape mapping. Unless you have some sort of example where you're trying to say, there is some notion out there that these things are different and we're coding them, we're showing here that they're really not different, right? If that's your case, then maybe this would work well. On the right, we do have a high degree of structure to our data set, and it tends to work well, right? We have green, orange, purple, pink, and then right around here, around 10, you can see all the shapes change from circles to triangles, right? And there is some size difference, I'm not sure, or maybe that's just two triangles that happen to line up like that, I don't know. But so here, right, you can see there is a clear separation between the triangles and the circles, and there's a clear separation for the different colors. So that one probably works pretty well. The left one doesn't work very well unless your point is to say that these really aren't different. Okay. Okay, on to the data to ink ratio. What is it? Has anybody heard of the data to ink ratio? I know some of you have because I gave parts of this talk to you in your psych class. Does anybody remember what the data to ink ratio is? Okay. It is, well, so this is a very famous quote by Edward Tufte, right? Above all else, show the data. And I believe that. I think that's a good goal. So he came up with this idea of the data to ink ratio, right? Which is the ink on a plot that's devoted to data divided by, right, the total ink used to produce the figure. So basically, how much of the stuff in this plot is related to the data versus how much of it is related to sort of extraneous stuff, right? And so a really common goal from this sort of idea was to maximize the data to ink ratio, right? So if you think about all the ink that's used to create your plot, and ink being, digital ink for us, then you want to have as much as possible that ink being devoted to the data, not other things, okay? So this is like an example where he came up with different versions of a box plot, right? And this was his version of the box plot that he liked, right? So this is the standard box plot, right? And this shows exactly the same information, but with much less ink, right? So, the median, the quartiles, and the interquartile range. So your first thought might be, cool, that's unique, interesting, different. But unfortunately, that plot, Tufte's, was the most difficult empirically for people to parse out. So this led many people to sort of go away from the data to ink ratio. And I would argue the data to ink ratio is still sort of a good thing to think about, but it shouldn't be the only thing that you think about, right? So Tufte's plot among those box plots was the most difficult for viewers to interpret. And that's because visual cues like labels and grid lines can help, they help you interpret the data, even though they reduce the data to ink ratio, right? So rather than thinking specifically about the data to ink ratio, what we should be thinking about is how can we minimize cognitive load, right? And so we don't want a bunch of stuff going on, because then there's too much for the person to focus on and they may miss the point of the figure because they're just overwhelmed with all of the things that you're trying to show. So this is another example where the one on the left minimizes the data to ink ratio. This one is, well, I don't know about minimizes, but it's lower, right? Whereas this one is higher. And so just looking at these two, which do you prefer? I'll let you think about that. This is advice from Wilke, our author of one of our books. Whenever possible, visualize your data with solid, colored shapes rather than lines that outline those shapes. And this is the important part. Solid shapes are more easily perceived and are less likely to create visual artifacts. Okay, and I think that's actually illustrated very well in this one, because you have these grid lines in the background too. So it almost looks like there's a second bar here, right? Or here, right? And here and here. But there's not, right? Those grid lines are there to help you sort of figure out the y-axis. But here you can very clearly see those are not different things, because this no longer looks like an additional bar because all the bars are blue, right? Does that make sense? But notice he also says whenever possible. This is not always going to be possible, because if you're publishing in a journal, for instance, they might say, no, we don't want solid shapes. Okay. Here's another example, and I would argue these are both great examples of visualizing some distributions with overlapping densities. They both show the different distributions by mapping it to an aesthetic, right? And they're also labeled directly, okay? So both of these are great. And this one would probably be better for a publication, whereas this one might be better for a, online publication or something. But this one I would argue is even better. And this is, again, where there's some artistic license here. Maybe you don't like this one, maybe you like this one more. But I think this one is easier to see all of the shapes. The one thing that's challenging about this one, however, is this one takes quite a bit more skill and tinkering to get right. Okay, this one's pretty easy to build, right? You just map color to the lines, whereas this one you're mapping the fill to the different species, right? And if you don't have your colors right, then it can introduce artifacts where this looks like a different distribution here or something like that, right? So this is an example where I think the colors work really well and the transparency level is good, so you can see each shape. But if they're too transparent or not transparent enough, then this might be less preferred to this one, okay? So I would still argue that you should try to do this if you can, but if you're having trouble and it's still not coming out right and you're not able to track it, then go back to one of these, okay? These are both great. And we'll talk more about text later, but this direct labeling like this of them is also super helpful in terms of minimizing cognitive load. This is basically an alternative to having a legend, right? So you don't have to have a legend anymore. You just directly label those things. And when you have only a few distributions like this, that's a super effective method. Okay, what about this? What do we think of this? Any thoughts?
I didn't even know it was a graph at first.
Right. So it looks like a monster, right? And because it's about monstrous costs. And so, your initial perception of this might be, well, this is silly, right? But the thing is, actually, that plot, a lot of people would say that chart has a lot of chart junk, but that plot is super memorable this is a really good example of basically an alternative to a bar chart, right? That's all it is, essentially. And so bar charts work really well, we know that. But putting it in this little monster's mouth actually was really effective because of monstrous costs, right? And so they showed this plot to a bunch of people. I think it was actually shown in the New York Times or something like that. It was for some campaign for somebody. And they went back months later and people still remembered this chart, okay? And that's probably largely because of this little monster guy versus, just a standard bar chart, okay? So the takeaway, right? It can often be really helpful to remove chart junk to make your plot as clear as possible. But again, this is just like an example of these are all rules of thumb, right? If you can produce something like this and it really matches your purpose, then that might be excellent. That might be the best thing that you can do because it's going to be more memorable. We're not going to be able to create something like that in R, right? But we could create the bar chart part of it in R, and then you could sort of embed it in something else. All right, so generally though, removing chart junk is going to help you. But infographics can often be more memorable. In some cases, you can use glyphs instead of points. This is disappointing to me, but I don't know why. This doesn't work anymore. So this part works, but I'll show you what doesn't work. All right, so you can install these packages if you want, and then we're creating data. This is about breached births. All right, so it's just a vector of 3 numbers. That's all it is. All right. Then we create a basic plot. Okay, so here's all the unbreached births and then these 2 other types. Okay, so this is kind of nice. This also actually has another visual artifact, which is you can see you get these little gray black dots between all the squares. So that's unfortunate. That's a visual artifact that we don't really want. I don't know why this doesn't work anymore, but it used to be, as of last time I taught this class, that you could add this bit of code where you would use extra font and font import and then load some fonts. And the reason I'm showing you this now is because even though it's not working for me right this moment, my guess is there's just some error. I spent probably an hour trying to get it to work. It still doesn't. But the packages will probably be updated and it will get fixed. Right now, it doesn't seem to work. If you're able to get it to work, great, let me know. But basically, we can take this and then assign it some colors again. But then all we do is say use glyph, and we say medkit. And then we get a plot that looks like this. Okay? And so this is, I would argue, a pretty effective plot, right? That's using, especially if your purpose is to communicate with a more general audience, because this is really no different than those squares, except now we don't have that visual artifact, and it's probably more memorable, right? So hopefully they fix that package soon. This is another example. This is from a Tidy Tuesday a couple of years ago, actually, but somebody used the patchwork package, which helps you sort of staple together different ggplot objects, and they were able to create this entire sort of infographic all in ggplot, right? Including these like sort of annotation things. And so this is another example that I think is nice in terms of showing like you can create infographic like things straight with ggplot if that's your goal. So this is just more example. Patchwork is a great package. Again, it's by Thomas Lynn Peterson. Cowplot will also help you. That's a good one. That's by Klaus Wilke, the author of our book. So both of these are good for stapling together different plots. Okay, we're not really ever going to have a lecture on doing that, but it's not terrifically difficult. You just need to read the documentation and sort of work through the examples, and you should be able to do it. And if you want to, and you're having trouble, let me know and I can help you through it too. Okay. All right, more visual properties. This is a really famous example, but basically A and B don't look like they're the same color at all to me, but they are. And this is supposed to help make it clear that they are the same color, and I still have a hard time personally seeing them as the same color. If I focus just on these lines, then I can see it as the same color, but as soon as I pull off from that, it still looks different to me. So we're not gonna do this, but I did embed a video where this woman shows this with an actual like board and actual light shining on this cylinder, and then she takes these squares and changes places, and you can watch it sort of change colors. So there's the reason I'm showing you this is because you have to be careful that your figures aren't introducing these visual artifacts that make it difficult, right? But you can also use those to your advantage, right? So in each of these plots, I'll just give you maybe 30 seconds here, and we'll stay here. But in each of these plots, there's one blue dot, okay? So look through these plots and see how fast you're able to find that one blue dot, okay? Ready to go. All right, everybody got it? Okay, so here, how long did this one take you? Like maybe half a second, right? Like it's obvious, it's right there, right? Even in this one where we have 100, it's super fast, right? Because that blue is so distinctive relative to those. Here, now we're varying shape instead of color, and it's quite a bit more difficult, right? So I had a hard time here finding this one, and this, well, not a super hard time, but this is only with 20. Once you get to 100, then it's quite a bit more difficult, right? And then here, in fact, where is it? There it is, right there. Here, right, now we have both colors represented, and we are trying to find the one circle that is blue, and it's right there, but that one's quite difficult, okay? So this is to show that we can use color to our advantage, and that our visual properties can see things like immediately, or it can take a while longer, whereas, right, this is varying color and this is varying shape between the two of these. And even though this one has 100, it's much easier than this one, right? And so if our purpose over here, maybe we needed to have both of those colors represented, but there's only one circle that we really want to highlight, we might want to just add one additional color that is just that one color. Maybe it's a bright pink or something that helps really pop that one out, okay? So this is sort of more examples of what we are good at perceiving. These are ranked, and these are empirical results. I'm skipping by this quick because we have a lot more to get to in only 5 more minutes. So we're not going to get through it all today. I'll just use a little bit of class next week to finish going through these. These are ordered mappings of some things. So this is like a good reference to come back to in terms of what's going to work well and what maybe isn't. So notice volume with 3D is at the very bottom. As a general rule, the more dimensions that you get into, the more difficult it is to track what's going on. That's why you'll not very often see like 3D scatter plots in the R world anyway, because this is pretty well known within the R world that those things don't work very well. They can work well to illustrate specific topics. Like I think if you're talking about multiple regression and you want to show the regression plane for 2 variables, that's a great example of it. But most of the time, it's going to work better to have 2 separate scatter plots that are in 2 dimensions versus 1 and 3. This is unordered data. All right. So real quick for the last 5 minutes here, I just want to talk about a couple of things to avoid. Okay. So line drawings, as I mentioned earlier, and this is probably not the best example because, as I mentioned, this is still a really excellent figure in my opinion. I would just preference this one, although the labels need some work on this one because they're bigger for some reason. So I would preference this one, but this one's still excellent. And there's ways that you can work to make them still really effective if you can't do full fill. Much worse is unnecessary 3D. Okay, and this is to the point where it's so well known that if you do implement 3D when it's unnecessary, then it's sort of a sign that you don't know what you're doing, basically. All right. So even beyond the fact that it doesn't work well, it's something to avoid just as like a signaling property to the people that you're working with. All right. So here's a quick example of why 3D, when it's unnecessary, doesn't work very well with the 3D pie chart, right? What we're trying to get at here is this area, right? And so it looks like a certain area here, but if we change the angle that we're looking at that thing, it looks a little bit different, right? And if we change it again, now it looks different again. So basically, we're adding unnecessarily here this perspective component that doesn't have any effect on the data that you're trying to show, but it does have an effect on what it looks like and how you perceive it. Okay, so you should not be using 3D because then you're adding this perspective element that doesn't actually relate to your data. Okay, even worse, and this is, I see this pretty darn commonly. This is from Microsoft Excel. 3D bar charts, right? So this bar is 80. That's what it is. It's 80. But it sure doesn't look like it if you follow this line for 80 across, right? This line is 105. Okay, so this is above 100. And if you follow that 100 line, it definitely doesn't look like it, right? The reason this is this way is because you have to follow this straight across to here, right? And then that looks like 80. And if you follow this straight across, then it looks like above 105. But basically what you're doing is you're comparing this front part to the line that's behind the thing, right? And so it gives this illusion that this bar or this column is below 100 when it's actually above it, okay? So this is like a really horrid example, and it's used a lot. Like I see these things pretty commonly. So avoid that as well, okay? Pie charts with lots of categories, I would also argue, are not good, okay? So here's an example where now you're basically trying to compare the angle of these things across these different pie charts. So here's E, and that one looks like less, and that one looks like less, but it's hard to know like how much less. And the other thing that's sort of difficult about this is they're all sort of in combination with each other, right? So as one increases, the other ones decrease, right? Because it's all sort of part of one thing. So here's an example where we're showing the same relation, but now with bars, and it's quite a bit more clear, right? You can track one across time to see what happens. So the yellow drops, right? The blue drops, the green goes down and then back up, right? And then the orange increases. But also within each of them, you can track across as well. This should not be confused to say that pie charts are always bad, though. I tend to not use them, and I used to actually advocate that you not use them either. But I have actually changed my feelings on this considerably after learning more about the research, right? There is absolutely a huge contingent of people out there that say never use pie charts, and I used to be part of that group. But the actual real empirical research does not say that they work bad. Like they're not bad if you have a low number of categories and specifically if your audience is used to them. So this is, I think, a pretty good bar chart or pie chart. Basically, a pie chart is just a stacked bar chart that has a radial coordinate system. So you could show the same relation like that or one of these. So this would still be my preference. But again, this is sort of, at this point, this is more of a artistic license thing. What do you like the most? Okay, so we'll leave off there. We'll start at dual axes next time. Quick, like sort of take home on what my message will be on dual axes. Never use them, ever. Okay, that's the message for dual axes, and we'll walk through why.